itself from a local unitary, but you can make the state plus some extra garbage, some conjugate or some inverse or whatever. You can make both of those from a short range, from a local unitary, and then you can just throw away one of them. You can just forget about it. And so in fact, Hastings showed that any gapped free fermion state is invertible. He actually constructed the inverse state and found a path in Hamiltonian space which maps this state plus its conjugate to a product state. And so then using the quasi-adiabatic machinery, you can construct this unitary. And so we conjecture that actually all SPT, including the ITO, well, I guess this doesn't include ITO, but SPT plus ITO, they're all of this type. So for example, the E8 state that we heard about today is of this type. If you take E8 plus E8 conjugate, the time reverse of E8, then you can deform that to nothing with a local unitary transformation. So this is the sense in which, coming back to your question, quantum Hall is actually short-range entanglement in the sense that there's no more entanglement that can be made with a single local unitary transformation. And so in that sense, this is almost but not quite a proof that interquantum Hall effect has no topological entropy. There's a subtlety which makes it actually not a proof. You would sort of morally, the quasi-local unitary seems to suggest you can't have any topological entropy, right? If you can calculate the entropy of this state is equal to the entropy of this state up to some boundary law thing. That strongly suggests that you can't have any non-local entropy. But there is some pathological counterexample which makes this actually not true. So it's close, but not quite a proof that SPT, formal mathematical proof that SPT states don't have any topological entropy, as we believe they don't. But yeah, so this is our definition of short-range entanglement. And it's essentially Kitaev's definition. It means no anyons. But I think it's nice because it makes contact with the circuit definition as well. It says the circuit definition is right as long as you're willing to have a little bit of garbage produced. For example, the opposite chirality interquantum Hall state. And one reason why we were interested in this is we were trying, again, part of the goal of the paper was to prove area laws, to prove the entropy is bounded by an area. And so we said, okay, the general area law is too hard because you could have states with ground state degeneracy, or even more complicated monsters where the ground state degeneracy grows with system size. But you should at least be able to show that for systems which are gap and have no ground state degeneracy, that just a single unique ground state, surely in that case, there's an area law. It's hard to imagine how that could not be true. And so I'll end today with a little quick argument for why that's true, which uses this idea of invertible states. And the claim is what we call the weak area law. There's all phases, again, meaning these sequences of Hamiltonians and ground states, is what we mean by phase. All phases with unique ground state of every manifold, closed manifold, obey the area law and have an inverse state. So here's the physics argument for this. The first part is to say that, okay, if the state has a unique ground state on every manifold, on every closed manifold, the only thing which could happen is some boundary degrees of freedom, right? It could be that I open the system up, opening expose a boundary, there could be some boundary effect. But nothing's happening in the middle. That's the first intuitive claim. But it's easy to get rid of edge states. You can always gap out the edge states. Here's the proof of that. Take your Hamiltonian H, which possibly has edge states. Take another Hamiltonian, which we call H reversed, which is just the orientation reversed Hamiltonian, or the time reversal of this Hamiltonian. Now, glue these two Hamiltonians together along their boundary. Because I chose this H reverse to be just the orientation reverse version of this, I can think of them, instead of as disks, I can think of them as hemispheres. The gluing just turns these hemispheres into a sphere. But by assumption, this system has a gap on any closed manifold. It has one ground state. So there is a way to take this system with edge states to find another system, the reverse system, which can glue just on the edge to produce a gap system. So for everything with a unique ground state and a gap on a sphere, but possibly the edge states on a disk, I can always take the reverse, glue them on the boundary, and form a gap state. And this gap state has all the same topological properties in terms of ground state degeneracy as the original. It has the same ground state degeneracy. In particular, if H had no ground states, then has only one ground state, then so does H reverse. So that means for any, so the claim now is that for any phase which has trivial ground state degeneracy but possibly edge states, I can make a new phase, which is just that phase plus its sort of reverse, which also has only one ground state but has no edge states. And now I can imagine doing something what we call the wormhole array argument. And that goes as follows. Start with the system. Now, this is your system of the system plus its reverse. So it's a two-layer system. And puncture little holes in this system. You can certainly do that. You can make a local perturbation of a gap system without closing the gap. And there's no edge state, so there's no reason why this hole is associated with anything interesting. Then we can expand the holes, right? The holes are far apart. They don't talk to each other. Everything's fine. We can now expand the holes. We can get the holes bigger and bigger and bigger. And again, at each step in the process, there's no edge state. There's no ground state degeneracy. Nothing's happening. So these are all gapped Hamiltonians. And so, although we don't explicitly prove that there's a path, we argue that there must certainly be a way to deform this gap state, which is completely trivial, to one with a slightly bigger hole. So you punch the hole, you make them bigger, bigger until they're almost the whole system, and then now you pinch off these little necks. And when you do this, what you then obtain is completely factorized product state. So in this way, we argue that as we turn this bilayer system of the system plus its reverse into a product state. And so in this way, we argue that starting over here, every such Hamiltonian with trivial ground state degeneracy, I can pair it with its reverse, I can get rid of the edge states, then I can do this wormhole array argument, and that's the end of the story. And the reason why we call it a wormhole array argument, let me just draw a little picture, is because if you draw this is H, this is H reverse. What we're really picturing is like putting little bridges. These holes here are like little microscopic bridges that tunnel between the top and bottom layer. And then we can expand them as big as we want because we've gapped the edge states out. So we expand these wormholes until they consume the entire universe, as it were. So this is a physics argument that all such states with a unique ground state on every closed manifold have an area law and are invertible. The area law follows from the invertibility. Because if you have the inverse, then the area law is true also of each of the states. So this is kind of the reason why we believe that E8, for example, is an invertible state. Because we believe that such a procedure can be done for that. Okay, so that's mostly what I wanted to say today. Tomorrow I'm going to tell you about a class of gapless Hamiltonians, an infinite class in all dimensions, where we can rigorously show that they also have the property of being S equal to 1. This class is not the most interesting class you've ever thought about. It's not CFT, it's not Dirac fermions, but it's, well, I'll explain tomorrow, but it's actually critical points with dynamical exponent bigger than 1. So like a Lifshitz theory would be in this class. And tomorrow I'll explain how to construct the unitary transformations for that class. And then I'll also tell you about our conjectures and work towards proving those conjectures for CFTs and for Fermi surfaces. And so I'll try to give you at the end a big picture of all different kinds of phases of matter we can encompass within this framework. And I'll emphasize again the same thing tomorrow, but the real point of all this, or one of the main points of all this, which I really want to emphasize, is the idea that given such a wave function represented in this way, it's possible to do calculations with it efficiently, in principle. And that's a big deal. So what we're really hoping for one day, we're not there yet, but we're really hoping one day is that we can take this kind of methodology and we can use it to actually solve, interesting models. And, you should contrast this with the tensor network literature, which has lots of hopes and dreams in it. It says we have tensor networks, they have the right entanglement, so maybe they can describe ground states. Here we just proved that they work. And so the hope is that this will encourage people to get into this field a little bit more, to really expend some effort and try to make these kind of ideas or other tensor network ideas useful for really solving interesting Schrodinger coupled problems in more than one dimension. And so, thanks. I'll see you tomorrow.
Thanks, Brian. So, any questions?
So, for this EA prime state, can you prove it only exists in 4n plus 2 dimension? In all the other dimensions, there's less like EA.
Yeah, I haven't tried to prove that.
And my second question is related kind of in other dimension, can you prove that this kind of tensor network representation can kind of faithfully represent all the topological physics? For this EA, it's a little bit tricky because somehow we have explicitly tensor network representation.
Yeah, so insofar as we believe E8 is S equal to 1, then it has this unitaries. And then we could always chunk those up into the circuit. So we can definitely write down a Mera which is close to the E8 state, and which, for example, has its energy density will be off by it has relative error of local quantities compared to the true state of any small thing you want.
I see, but you need a mirror. The simple translating mirror.
Well, you can always you can smush the Mera into PEPs in 2D. So actually, we conjecture based on this that.
But then this dimension could be infinite.
No, it's not infinite. It grows, but it's not infinite. Not in 2D. In 1D, it could be infinite, but in 2D, it's not infinite. The number of links that cross any given sort of PEPs bond is finite. No, it requires you to route things in a confusing way, like to assign the links in a strange way. But just because the counting of the entropy is the same, it has enough degrees of freedom.
So do we have a precise write out this tensor precisely?
In principle, we could. We haven't done it yet, but we conjecture that there is actually a constant bond dimension wave function which is in a quantum Hall phase.
Yeah, actually, there are some work by Serac and Goury.
Yeah.
They are finding that in terms of this kind of Gaussian paths, it have the problem of this gapless.
Yeah.
You're not considering this constant gap or something.
What we don't know. I have an argument that it's gapped, but we don't know. So there are various arguments saying that this is not possible, and there's all this evidence.
But
we have a construction. And it looks to me like it could be possible.
But their claim, I think, limited just for this Gaussian path.
Yeah, I think there's no reason why it's true. So you just take this, take the unitary, make a Mera out of it. That will have very close to the right energy density. So by the stability of the phase, there should be another Hamiltonian nearby, for which this is actually the exact ground state. And that Hamiltonian, could just be the usual parent Hamiltonian. So I strongly believe this Hamiltonian is gapped, and that its exact ground state is Mera as given, and that Mera is essentially the E8 state. So I actually believe that this is true, but it would be really nice to check this.
At least if you have the exact with the tensor, you can compute like the correlation function.
Yeah.
Yeah.
Yeah, I mean, everything will, I think, be fine, yeah. So I actually believe that there is actually constant bond dimension PEPs, but we can't prove it yet.
Perhaps one more quick question. If no more, let's thank Brian again. So we'll be back at 3.